Right. So you had to plot for phi ref of t equal to 0, which would give you the ideal square wave, then a DC value, then a cos of omega ref t, and then harmonics of that. So let me consider the cases. So phi ref of t is a, I'll call this as 1. Then this was a cos of omega ref t, then a cos of twice omega ref t, and finally 4 times omega ref into t. Okay. So let us consider an ideal square wave. Now, if I were looking at phi ref of t, I will simply sketch it out for all the cases above. So first case is where the value is simply a. Now, the second case is where you will have a cos waveform, which will have the maximum value at these points and the minimum value here, 0 crossing somewhere here. Assume that this is a cos waveform. And then 2 omega ref of t. So what would be the value corresponding to these points? So it will start like this, right? Right. And 4 omega ref of t will be, you'll have 4 times the waveform within this period. So I'll plot it only for points that are relevant to us. So at these points, right? So in the first case, your square wave is simply going to shift by some amount. Let me call this delta t. Can you calculate delta t? What would be delta t? So it will be a upon 2 pi into t ref, right? So this is delta t, and here it will delay by delta t. Sorry, it will advance everywhere. It's a constant. Yeah. So it is going to advance by delta t in all these points, right? Now, if I take case 2, so this is 3. What happens for case 2? At this node, it is going to advance by delta t. Here, it is going to delay by delta t. Here, it is again going to advance by delta t. Case 3, all these edges are going to advance by delta t. Case 4, again, everything is advanced by delta t. Right? Now, if I were feeding a signal like this to my delay lock loop, and a delay lock loop can detect only the rising edges, right? Can it differentiate between DC, omega ref, 2 omega ref, 4 omega ref, etc.? Can it differentiate? Yes, no, maybe. So let me remind you what a delay lock loop is. We have ref of t. Can this loop detect any difference between the 4 cases that we discussed? So we have a small signal phi ref of t here, and we are looking at different frequencies for it. One is it's DC, then omega ref, 2 omega ref, 4 omega ref. It cannot detect. Why? Because this is a sampled system. So we derived a continuous time model for this in Laplace domain, right? So what comments can you make about the validity of that Laplace, validity of the S domain model that we got? Up to what frequency can you rely on that model? So I'm plotting, let's say, h of s at j omega versus omega. Is there a particular frequency for which I can rely on this model, beyond which I shouldn't take the results from this model seriously? What comment can you make about that frequency? Is it omega u? Why omega u? After that, gain will decrease, yes, but so what? I mean, this model is telling me that the gain is decreasing. How do I know whether it is valid or not? I'm just looking at whether I can rely on this model. So the model is telling me something. Up to what frequency can I rely on the results? You mentioned omega rf, right? Why omega rf? Right. So why do you say omega ref? Why can't it be omega ref by 2, omega ref by 3? Does this bring back some memories about a theorem that you have learned? Why? Right. So if you have a signal and you are sampling it, right, what is the rate at which you have to sample the signal to capture all the information? Twice the maximum frequency in that, right? So now we are sampling it at omega ref because that our rising edges are coming at every t ref, right? So our sampling rate is f ref or omega ref, right? So I can rely on this model up to omega ref by 2. Okay. At omega ref by 2. Okay. So the feedback is not there. That part is correct. But no, please complete your question.
Need to be very large as compared to omega.
Correct. Correct. So omega ref will be larger than omega u. Okay. So
like we cannot rely up to omega ref by 2 because the exact frequency for sufficiently high frequency feedback isn't there. So it's working like that.
So this is not just about the regions of frequency where you have very high loop gain, right? It's about knowing the full loop dynamics. For example, we know that if I inject a noise at the PFD, it has a low pass transfer function. So if the noise is getting injected beyond omega u, it is going to see some attenuation. Right? So which means that any high frequency noise getting injected at this point will get filtered out. Due to capacitance, yeah, it is getting attenuated. There is no
point of injecting any noise. It won't have any effect, right? I mean,
so we are not injecting the noise. The noise is present in the circuit. Right. So now how we choose this omega u is actually an interesting problem because any VCDL noise is going to see a high pass shaped transfer function. Any PFD noise will see a low pass shaped transfer function. Right. So now if your VCDL noise was the dominant noise, then you want to filter it as much as possible. So how should you choose your omega u? So let's say VCDL noise is very large. How should you choose your omega u then? We have to choose a large omega u because this has a high pass shaped transfer function. So if I shift this omega u to this side, it means most of the VCDL noise will get filtered out. Right? So it is not just that there is low gain at very high frequency. Now that information is useful to us, because we can then play around the value of our omega 3 dB such that we can optimize the noise appearing at the output from VCDL as well as from the PFD. Our aim is to, in most cases, the small signal we talk about will be jitter, an unwanted quantity, and our aim is to filter it out as much as possible. Is that clear? So we are now not, we are simply looking at how much we can rely on the model that we have obtained. Okay, so any results you get from the model up to omega ref by 2, you can use it. Beyond that, we have to understand that this model has major limitations. One is it is not capturing the sampling behavior. And the other part is we optimized this. We said that the delay present here, e power minus s into t ref, is much smaller compared to the settling time of the loop, and we ignored it. Now, if we ignore it, then we get a transfer function like this till omega rf by 2. If we don't ignore it, then you'll see that there is a peaking in the performance. This is okay. Now, this is about the model. So Pankaj had asked an interesting question last class. Whether this behavior, so I'm looking at the magnitude of h of s at s equal to j omega. Now, this is a DLL. Nothing is preventing me from giving a phi ref at different frequency and looking at the phase information at the output. Okay. So now this is not about the model. I am giving some phi ref of t at the input, varying its frequency, and I'm looking at the phi out of t at the output. How do you think the behavior would look like? So up to omega ref by 2, the model is predicting this behavior. What do you think will happen afterwards? Okay, can you tell me, if I give a phi ref of t with frequency at omega ref, how would it look like, the output? It will look like DC. So if the frequency is omega ref, we just saw earlier that there is no difference between that and the DC value. So you will see the same result as the DC here, right? Now you'll get the same result at 2 omega ref. And we just said that this is now aliasing. Like if I have 5 of omega ref t, that information is getting aliased to DC, right? So basically the whole function will look like this now. So you can expect to see periodicity in this pattern. Okay.
You say will always be positive, and can't we see that?
It will not be negative. So now let's analyze the system with discrete time domain model, and then you'll be able to see that the peaking can never be, it can never be an attenuation, right? So we'll now look at discrete time model for the DLL. Okay. So the main motivation of going to this discrete time model is so that we can capture the sampling behavior into our model, right? So if I have phi ref of t, the DLL is simply looking at phi ref at n times t ref, correct? Which means I can simply look at a sequence of phi ref of n, where for each value of n, I obtain the value by sampling this phi ref of t at n times t ref. Okay. Similarly, I will have a phi out of n, a VC of n, etc. Okay. So now first, let us see how to do the VCDL model. So you basically have a phi ref of n going to our VCDL. This also has a VC of n as an input, and the output is phi out of n. And we now have to model the relationship between phi ref of n to phi out of n and VC of n to phi out of n. So I'm going to write this directly because we discussed this for the continuous time in detail. But phi out of n will be equal to phi ref of n minus 1, because we expect to see a delay of 1 period, plus KDL into VC of, what should it be? n minus 1, because you make a change in VC, we can measure it only at the next edge when the output edge comes out, right? So you can expect at most 1 period delay. Now, once you write like this, it becomes very easy to get the Z transform. So this is equal to phi ref of Z into Z inverse plus KDL into VC of Z into Z inverse. So now I can model this. So I have a phi ref of Z. So I can take the Z inverse from both sides together like this. So phi ref of Z plus, so VC of Z goes through KDL, and then it sees a delay of Z inverse to give me phi out of Z. Okay. So now let us model PFD plus charge pump plus the loop filter. So phi error of n. So phi error of n is the delay, the phase error seen at the input of the PFD. Then we have a charge pump with nominal current ICP and then a capacitor. And then we are looking at the small signal voltage developed here. Okay. So can you tell me the expression for phi error of n? So this is phi ref of n. And here you have phi out of n. In terms of these two, can you tell me the expression? BC n minus 1. Why? Okay. That is correct. But now I have this thing in open loop, right? I'm modeling only this part. Summation of. So phi error of n, yeah. So phi error of n in terms of pi ref of n and phi out of n. So this will be, correct me if I make a mistake here, phi ref of n plus phi out of n. It has to be minus. Yeah, we are finding the difference, right? So in time domain, we wrote it as phi ref of t minus phi out of t. So it's phi ref of n minus phi out of n. Okay. So now I can write my VC of n as some existing VC of n. So from the previous cycle plus some charge that is pushed into it divided by C. This is okay. So now I just need the expression for Q of n. Can you tell me that expression? So we'll start with phi error of n divided by 2 pi multiplied by ICP So okay. So now charge has to be some, if I'm writing it in terms of the current, it will be some I into delta T. Right? So I have the I here, ICP. Now I need to know the duration for which the ICP is getting pushed into the capacitor. Right? So what would that duration be? So ICP is flowing into the capacitor for a short duration. It's not flowing throughout the period. What is that duration? What does that correspond to? Can you tell me in terms of this phi error? Phi error by omega ref. Is that clear? So phi error is the phase difference between up and down. Sorry, between the reference and out. And corresponding to that phase difference, we have ICP flowing into the capacitor. So now I have to convert phi error into some delta t. So that will be phi error by 2 pi into T ref. Right? So phi error by 2 pi into T ref. Okay, and for this duration, we have ICP flowing into the capacitor. This is clear? So now I can write the relationship between Vc of n and phi error of n. This will be equal to Vc of n minus 1 plus 1 by C into ICP by, so I'll make it as 2 pi C into T ref into phi error of n. Okay. So I can now take the Z transform. This is Vc of Z plus Vc of Z into Z inverse plus ICP T ref by 2 pi C into phi error of Z. So can you give me the relationship between Vc of Z and phi error of Z? What do you get? Some confusion? So this divided by 2 pi C into 1 by 1 minus Z inverse. Right? So this is phi error of Z. Let me start from phi ref of Z. This is equal to Vc of Z. Okay. Now, can you do the DLL model completely? So you know how PFD CP model is PFD CP plus capacitor can be modeled as. We have seen how VCDL can be modeled as. Can you put everything together? Please try. So if you have already derived this, please calculate phi out by phi ref. So you can calculate phi out of Z by phi ref of Z. You can assume that ICP T ref by 2 pi C into KDL. Call this variable as some alpha and then derive it. So please start deriving this. Did you get the following expression? Okay, so now that you have a expression like this, so this is a closed loop systems expression. We have a pole in the system, and this is at Z is equal to 1 minus alpha. What is the stability condition? This has to be inside a unit circle. So that means the magnitude of 1 minus alpha has to be less than 1. So I can write it as 1 minus alpha should be between -1 to +1. What condition do you get on alpha? You will get a lower limit and an upper limit based on this. What are the conditions? So alpha has to be greater than 0 and it has to be lesser than 2. Now alpha greater than 0 simply means that this quantity has to be positive. So that ensures negative feedback in the system. If that quantity becomes negative, your feedback becomes positive, right? So alpha greater than 0 simply means it is simply ensuring that the system is in negative feedback. Let's analyze the second condition, which is alpha lesser than 2. So in this expression, is this quantity looking familiar? ICP KDL by 2 pi c. This was omega u for your continuous time derivation, right? So I can simply write it as omega u. I'll put CT to remind you that it is from the continuous time derivation into T ref is lesser than 2, which means omega u should be lesser than 2 by T ref or 2 into F ref, which is twice omega ref by 2 pi, or in other words, omega ref by pi. So this is actually a stability requirement. Your omega u should be smaller than omega ref by pi. Now we said that we generally design with omega u lesser than omega ref by 10. Right? And we said that once we satisfy this, the Laplace domain model is approximation is valid. Okay. So if you have already designed with this, you are automatically satisfying the stability condition. But the fact that this system could become unstable, this is not very evident if you only analyze the Laplace domain model. Okay. And that comes out because of the sampling inherent in the system. Okay. So now I can also calculate the magnitude of h of z. So we'll be calculating at h of e power j omega. Now let us calculate this for two frequencies. So we are now looking at the discrete time frequency 0 that corresponds to DC and pi. What does pi correspond to in continuous time? It's sorry, Tref by 2. Basically 2 Tref corresponds to omega ref by 2. Sampling frequency by 2. Right? So if my omega equal to 0, what is the value of z? Z is equal to 1. For omega equal to pi, z is equal to -1. Now, can you put this information in the h of z and tell me the values? What is the magnitude when z is equal to 1? It's equal to 1. Okay. And what about the second case when Z is equal to -1? So you'll have to tell me the expression in terms of alpha. Sorry, Z is equal to -1. You should get 2 plus alpha by 2 minus alpha. Is this greater than 1 or less than 1? What is the range of value alpha can take? 0 to 2, right? So is this going to be greater than 1 or less than 1? It's going to be greater than 1. So this will start from 1 and then this is going to peak. Okay, so this answers your question whether you can get a attenuation around omega f by 2. So this proves that you will always have a peaking. And this is what we call as jitter peaking, because if your input signal had a jitter, that jitter will be amplified by the DLL. Right? And if you want to suppress this jitter peaking, you can never make it 0 because alpha has to be greater than 0, right? So jitter peaking is always existent. And to make it minimal, you will have to reduce the value of omega u. So the time taken for the DLL to settle will increase if you want to minimize jitter peaking. Okay, so is the discrete time model clear? Okay, so then let's get back to our flash TDC implementation. Do we have any solutions? So our flash TDC had a stop and a start signal. So stop was like this. And we were delaying the start and then looking at the sampled values. Now, the problem with this implementation was that we were relying on the buffer delay for our resolution of the TDC, and this was a function of PVT. So we came up with this delay lock loop circuit to stabilize this. But now how do I put both the information together? Can I make this as my VCDL? I make this as a part of a DLL, is it? Okay.
Then we can replace
So we can't directly make this as a part of the DLL because once you do that, where will you feed the start signal? Right. So I can, of course, make a delay line. So this is assume a VCDL. All of these are tunable delays. And then I can use the feedback. So PFD plus charge pump. Then I will have this information on a capacitor. So this is going to generate a VC voltage. And then I feed this VC to all of these buffers. Okay. Now, if this is my DLL, this has to be a clock, a reference signal. I cannot feed the start signal here. We need a repetitive signal here, a signal with repetitive rising edges with a period of Tref so that I can achieve the delay of Tref across this delay line. Correct? If I feed a start, which is probably a one-time event, I will not be able to establish a good feedback around this. Okay. So once I do this, the delay of each element will be now equal to Tref by N, assuming N identical buffers. Now what can I do? So we make sure we design these buffers as identical buffers as that of the delay lock loop. Then I supply the same VC voltage to all of them. Right? Now, if this delay line and this delay line are identical, then our resolution will now become Tref by N. And when I say identical, it has to be exactly identical. So I will have to put dummy loads here. So that the load seen at this node and the load seen at this node would be identical. So you'll have to place dummies everywhere. And then you have to make sure that these two delay lines are placed close to each other. They are identically laid out, etc. So that all the parasitics seen by both the delay lines are same. So this is now the original delay line. And this is what we call as the replica delay line. This is okay? Okay. So we can stop the class here. If you have any doubts, you can ask.